Now we need to get a 0 in the first entry of row 3. So we need to eliminate this 6. So let's multiply row 1 by 6 and row 3 by -5. Then we'll add the two rows together and replace the old row 3 with our brand new row 3. You should push pause, execute this plan, and then come back when you have your new row 3. Are you back yet? Let's buzz through this plan to see how you did. Did you get 0, 7, -1, 6, 0, -5 for the new row 3? If not, try again. Okay, now we just need to rewrite the matrix so we can replace the old row 3 with the new row 3. Again, we keep the rows that we did not plan to replace and then ignore the old matrix. Let's move the new matrix up and move on to the next step. Now remember, we're still trying to force all the entries below the main diagonal to be 0. So we need to eliminate the second entry in row 3. To eliminate the second entry, 7, in row 3, what do you think our plan should be? Be careful, if you use row 1 to eliminate the 7, we will lose the 0 in the first entry of row 3 when we add the two rows together. You'll need to use row 2 to help get rid of the 7, as the first entry of row 2 is also a 0. So let's multiply row 2 by -7, multiply row 3 by 26, and then add these rows together to get our new row 3. Push pause, execute the plan, and come back when you have another brand new row 3. Did you get 0, 0, -5, 135, 35, -130 as the new row 3? So did I. Okay, so you know the drill. We rewrite the matrix, replacing the old row 3 with this new row 3. Whew! All the entries below the main diagonal are zeros. Let's move this matrix up and work on the entries above the main diagonal. We need to eliminate the third entry, -3, in row 2, but we don't want to lose the 0 we have in the first entry of row 2. So we'll need to use row 3 to eliminate the -3 in row 2. Push pause and try to write the plan for eliminating the third entry in row 2. Did you get 5 times row 2 plus -3 times row 3 to replace row 2? Or possibly -5 times row 2 plus 3 times row 3 to replace row 2? Either plan will work, as both will eliminate the third entry in row 2 while preserving the 0 in the first entry of row 2. So that we get the same results, push pause and use the first plan to get the new row 2. Did we get the same result? Is your new row 2 0, 130, 0, -390, -130, 390? All right, let's go ahead and write our new matrix, replacing the old row 2 with this new row 2. I'm getting a little tired of all this heavy lifting with those big numbers. You know, the elementary row operations allow us to multiply any row by a non-zero constant. And I happen to notice that 130 evenly divides each entry of row 2, and that 5 evenly divides each entry of row 3. So let's take a minute and clean up the matrix we're working with. Let's multiply row 2 by 1 over 130 and put the result back into row 2. Then let's multiply row 3 by 1 over 5 and put the result back into row 3. Now we can make some room and move this last matrix up. Okay, keeping in mind that we need each entry above the main diagonal to be a 0, we realize that we should eliminate the third entry in row 1 next. Wow, cleaning up that last matrix sure makes this easy. We just need to multiply row 3 by 4 and add it to row 1. Go ahead and push pause to execute this plan and find the new row 1. Did you get 5, 7, 0, 109, 28, negative 104 for the new row 1? I did too. Let's rewrite this matrix with our new row 1. Now we only have one more entry above the main diagonal which needs to be 0. To eliminate the second entry in row 1, we simply need to multiply row 2 by negative 7 and add the result to row 1. Push pause and come back after you find the new row 1. Did you get 5, 0, 0, 130, 35, negative 125? If not, push pause and try again. Okay, we're almost done. Let's rewrite the matrix with its new row 1. Oh, look! The matrix on the left is almost the identity matrix. We just need to force each entry along the main diagonal to be a 1. To do this, we need to multiply row 1 by 1 over 5 and row 3 by negative 1. Now let's make some more room and move this matrix up as well. Since we have the identity matrix on the left, A inverse must be the matrix on the right. However, if we were unable to obtain the identity matrix on the left, i.e. if one of the entries along the main diagonal ended up being a 0, then we would say that A has no inverse.